Welcome to the Explainer, everyone. Today, we're strapping in for literally one of the most mind-bending cosmic mysteries in all of modern astronomy. Seriously, we are going on a grand investigation, piecing together clues scattered across hundreds of millions of light years just to track down an invisible culprit hiding in the dark. It's this massive story of mind-boggling gravitational forces, blocked evidence, and a universe that's just so much more dynamic than it looks from our backyard.
Okay, let's dive into this. Look at that number, 1,300,000. It's a huge number, right? Well, right at this very second, you, the Earth, the Sun, and our entire Milky Way galaxy are hurtling through space at roughly 1.3 million miles per hour. We aren't just sort of randomly drifting either. We are speeding through the cosmos in a very specific, deliberate direction.
Which brings us to the visceral question anchoring this whole investigation. What on Earth, or I guess what in the universe, is pulling our galaxy through space with such staggering force? To figure that out, we essentially have to play cosmic detective and read the clues hidden in the motion of the stars.
Section 1. The million-mile-per-hour mystery. Before we can pinpoint our prime suspect, we really need a quick refresher on how things actually move out there in space. Because, it's not as simple as just flying in a straight line. In cosmology, we basically have two main types of motion. First up is cosmic expansion. That's the Hubble-Lemaitre law, where the universe is uniformly growing, stretching space itself, and making galaxies recede from each other. But then, we have what astronomers call peculiar velocity. This is a local deviation caused by the gravitational pull of nearby mass. Think of it like a treadmill. Cosmic expansion? That's the treadmill belt constantly moving backward. But our peculiar velocity is us actually running forward on that belt, being drawn by some massive gravitational weight right in front of us. So that 1.3 million mile per hour sprint we're doing, that's our peculiar velocity.
Section 2. The zone of avoidance.
And this brilliantly illustrates the big problem. If we know we're being pulled, why not just point a telescope in the direction we're headed and, well, look at what's pulling us, right? Well, every good detective story has an obstacle. See, our Milky Way is a flat, disc-shaped galaxy, and we live right inside that disk. When we try to look out at the wider universe in the exact direction of our cosmic motion, we have to look straight through the thickest part of our own galaxy. The dense interstellar dust, the gas, the billions of foreground stars, they act like a massive brick wall. It effectively creates this gigantic blind spot covering roughly 20% of the entire extragalactic sky. We call it the zone of avoidance. For decades, whatever was pulling us was hiding perfectly right in the shadows of our own galaxy.
Section 3. The Seven Samurai.
But as you know, astronomers don't just give up. If optical light was blocked, they were going to have to map the flow using other clues. Back in the 1970s, we started getting these early hints of large-scale motion, stuff like the Rubin-Ford effect. But the real breakthrough hit in 1987. A group of 7 brilliant astronomers, famously dubbed the Seven Samurai, studied the scaling relations of about 400 elliptical galaxies. By measuring how these galaxies were moving completely independent of cosmic expansion, they mapped out this coherent, massive stream of galaxies, all flowing toward a previously unrecognized mass concentration. It was astronomer Alan Dressler who gave this unseen gravitational titan its incredibly catchy sci-fi-sounding name, the Great Attractor.
Now let's clear up a massive misconception right off the bat. Despite that incredibly dramatic name, the Great Attractor is not some 1950s B-movie space monster eating galaxies, and it's definitely not a single ultramassive black hole vacuuming up the universe. Actually, scratch that. It's more like a broad gravitational basin. It's an immense structural feature of the universe, heavily dominated by invisible dark matter, acting as a collective center of mass. We're talking about a localized valley drawing tens of thousands of galaxies inward.
Section 4. Unveiling the Great Attractor.
Now, what's really interesting about this discovery is how we finally saw it. The Seven Samurai proved it was there, using math and velocity maps, but to physically see the Great Attractor, we had to pierce the veil of the Milky Way. Visible light gets absorbed by all that dust, but other wavelengths, they slice right through it. By using X-ray surveys like SESA, infrared surveys like Spitzer and TUMAS, and radio telescopes mapping out neutral hydrogen, astronomers peered straight into the blind spot. And what did they find lurking right near the core of the Great Attractor? The Norma cluster, also known as Abell 3627. It's this incredibly massive, dense cluster of galaxies roughly 220 million light-years away, just violently dragging surrounding galaxies into its hot, X-ray emitting core. To put that into perspective, the scale here is just staggering.
Our Milky Way is huge, right? But it's literally just a speck compared to the mass concentrated around the Great Attractor, which essentially acts as the gravitational focal point for our local Laniakea supercluster, a web containing 100,000 galaxies. But here's the thing. A glaring issue emerged in the data. As incredibly massive as the Great Attractor region is, we're talking around 10 to the 16th solar masses in early estimates. When astronomers actually tallied up the visible and X-ray mass, it just wasn't quite enough. The Norma cluster alone simply could not account for our blistering 1.3 million mile/hour speed.
Let's move to Section 5 and see how this builds the ultimate cosmic twist.
Because every great detective story needs a plot twist right when you think you've solved the case, right? Well, here it is. The Great Attractor? It's just a middleman. Our massive sprint through space isn't caused by one single culprit at all. As we mapped further out, we found the shapely supercluster sitting way behind the Great Attractor, boasting 4 times the mass and pulling both us and the Great Attractor toward it. Plus, we recently uncovered the ghost-like Vela supercluster hiding even deeper in the zone of avoidance, adding to that pull. And no way, it gets crazier. It's not just about pulling. We are also being pushed. A massive, desolate region of empty space called the dipole repeller void is effectively pushing our local galaxy flows away from its empty center. We are quite literally caught in a gigantic cosmic tug-of-war, and we're honestly just starting to map the battlefield. Upcoming next-gen observatories like Euclid, the Vera C. Rubin Observatory, and the Square Kilometer Array are going to peer even deeper through the dust to finally untangle this whole shebang.
I absolutely love this quote from Kolokithis because it perfectly captures the essence of our explainer today. In cosmology, mass is destiny. Gravity acts as the ultimate architect of the cosmic web. Over hundreds of millions of light years, matter clumps together, forming superclusters and walls of galaxies that create these immense gravitational basins. Our Milky Way is essentially just a drop of water flowing down a cosmic mountain, entirely directed by the massive topology of the universe.
But here is the ultimate cosmic punchline. We are hurtling towards the Great Attractor, for sure. So the crucial point is we will actually never, ever arrive. Yep, because while our peculiar velocity pulls us toward it, the overall expansion of the universe, driven by that mysterious dark energy, is stretching the space between us faster than we can cross it. In reality, we are currently receding from the Norma cluster at roughly 4,700 kilometers per second. Going back to our analogy, the treadmill is moving backward way faster than we can ever run forward.
Which leaves us with this final, genuinely provocative thought. If dark energy continues to accelerate the expansion of the universe, will these magnificent gravitational basins, these great attractors that have literally shaped the destiny of our galaxies for billions of years, eventually just be isolated, stretched, and completely torn apart entirely? The Great Attractor reveals a universe in constant, violent motion, but its ultimate fate is a mystery we're only just beginning to unravel. Keep looking up and keep exploring.